So next up, Ian Parry, who's going to be telling us about SUPERSHARP.
So I'm going to talk about a telescope concept called SUPERSHARP, which is basically an unfolding telescope to go into space. So here I've also listed my collaborators, my small team. And so this project is getting a little bit of momentum now. It's not just me doing it. There's a few other people as well. So and this is a picture of a 3U CubeSat version of an unfolding telescope. I'll come back to that later in the talk. So to start at the beginning, I got into this because I'm really interested in the scientific question about searching for life, asking the question, are we alone in the universe? Can we look at exoplanets? And can we investigate them to see if they have biosignatures in their spectra? So that's where I got started with this. And if you want to look at 100 exoplanets and check them out to see if they have biosignatures in their spectra, then you need to look at about 1,000 habitable zones that you can resolve. And to see that many resolved habitable zones, you need lambda of d to be small enough, which means d needs to be quite big, and it turns out that it needs to be about 12 meters or so. So simply to do this experiment, you need a big telescope. And of course, that's bigger than the rocket fairings that we've got. And so, we're going to have to unfold it to fit it in the rocket to launch it. The technique is basically high contrast imaging plus high resolution imaging and integral field spectroscopy. So it's a bit like SPHERE or GPI on a big telescope in space. And as I've just said, you're going to have to unfold simply to get it up there. So this led me to what I'm going to describe, which is the SUPERSHARP concept. It does actually stand for something. I won't bother reading it out. And if you want to know more about it, there's a paper on AstroPH. So I'm relatively new to this game. People have been thinking about this biosignature search for decades. Sorry, so I'm very new to this. So the consensus view is that this is going to be done by NASA. It's part of the decadal review coming up. It'll basically be the successor to JWST. It'll be a flagship observatory, probably a similar model to HST and JWST in the way it's operated. And it's going to be big. There is a small version called HABEX, which basically is an external coronagraph, so you don't need quite such a big telescope because you do the high contrast imaging with an external star shade. I'm not really going to talk about that. I'm really talking about more about the LUVOIR approach, which is the proposed successor to JWST. So things in black there I'm fine with, but now I'm getting to the 2 points where I'm not very happy about them because optimistically this plan is going to take at least 16 years and probably realistically 25 years, so it's going to be a very long time before it actually starts happening, and it's going to be very expensive. So I started thinking about this because people have already been thinking about this for 2 decades, and we're still talking about 2 decades before it happens. I felt perhaps we should just be getting on with it. We know how to do it, so why don't we just get on with it? Plus, I'm getting on a bit as well. I'd quite like it to happen before while I'm still around to appreciate it happening. So there's some pictures here. This is LUVOIR, I just mentioned, 12 or so meter telescope. Can do direct imaging, take pictures of systems like our solar system if they're out there. I won't say much about HABEX. I'll move on. So how does my idea about SUPERSHARP differ from LUVOIR and JWST? I mean, LUVOIR and JWST are quite similar in many ways. So basically, a fundamental difference is that I suggest that we abandon the fully filled aperture. We've already seen from sparse aperture masking from Sasha this morning and the interferometer people that this is not a new idea. Lots of people are already doing it for high-resolution imaging. Basically, it's all about maximizing D. You don't really care too much about filling the aperture. You want to maximize D. So I think that's one thing you want to do. Secondly, you want to make the structure as lightweight as possible so that you can pack as much telescope into your rocket, and so make it lightweight. That means it's relatively unstable, has drift scales and so on, time scales. So that means it needs to self-align. It needs to be able to measure its own errors and correct them continuously. So this is a bit like adaptive optics, except that the light source is inside the telescope and it's continuously correcting itself. So essentially those top three technical differences amount to this. Basically, we're trying to maximize the launch density, put as much telescope as we can into the whatever size box we've got for launching, and have it open up, and therefore sort of minimizing the operational density and maximizing the size of the telescope that you get at the end. So this is basically what IKEA do, right? With their furniture. Flat pack for moving it around and storing it, and when it's deployed, it's full of air. Space in this case. Okay, so those are technical things. The fourth bullet point here is more of a strategic thing. Now, we all love NASA and ESA. They've all done wonderful things, but we don't really think that they're famous for being quick or inexpensive. Right? And I think nowadays, because we're in a new modern era of space operations, there are now alternatives to funding sources that we need to think about using. I'll come back to that in a minute. So the technical challenges are that you need to be able to unfold with a certain amount of accuracy, but not a huge amount of accuracy. It just has to roughly get in the right place. And then you need precision actuators to take you from the rough unfolding accuracy to the very high accuracy that you need to make it work as an optical system. And so you need a precise metrology system so you can measure your errors. You need very high accuracy actuators so that you can correct the errors that you've measured. And you need a sophisticated control system to make that close the loop. So this is a very simple cartoon of how the thing works. Here are two rays coming from space. Here's our primary mirror, which is segmented, has gaps in it. And the light from there goes to some imaging system shown here as a prime focus system. It doesn't necessarily have to be. It could be a secondary mirror with an imaging thing over here. But it basically, there's a focus somewhere focusing on the things you're interested in. But in addition to that, we now add a metrology system at the center of curvature of this mirror. So light from here, when it goes onto the mirror, will actually go back to the metrology system. So this can measure accurately where all these optics are. And it can also measure where this is too, right? Because you can send light from there onto this. You can have a mirror here. And so you can do metrology of that piece of the optics as well. So you can basically measure where everything is. And if everything has actuators on it, you can correct it. That's the basic philosophy of SuperSharp. So here's a picture from the white paper I talked about a few years ago now of what it looks like when it's deployed. For the exoplanet biosignature search, you need a big baseline. This is 24 meters across from here to here. And the mirror is this cross-shaped thing here, and it's made of segments like that. So that's the mirror. The center of curvature metrology system is up there. The imaging system with a coronagraph and the integral field spectrograph would be here. And then all the other housekeeping stuff is there, and you've got something to stop the sunlight messing up the observations. And here's let's see if I can make this work. Can I make this work? Yep. Here's a sort of animation of how that unfolds. So it's a bit slow. In this particular one, the mirror unfolding is separate from the tube unfolding. Okay, so and that's how basically this was a concept. It was basically to show that the items would fit inside the rocket, and that in principle you could actually make it all unfold. And then I did some simulations, and that thing there is an actual exoplanet, a simulation of a super-Earth in the habitable zone of a fictitious nearby G-star. And that's just one channel of the spectrum that you need to take. So this telescope concept does deliver the science. So how do we actually go from an idea like this into reality? Because this is a huge project, and there's no way, if I just write a proposal now, say you can give me millions of dollars to build this, there's no way that's gonna ever be funded. We need to figure out some way of doing this in smaller steps. So if this works, it actually has a lot of applications. It's not just useful for the exoplanet biosynthesis search. It has a lot of applications. Basically, the bigger the telescope, the sharper the images you get because of lambda over d. And so if you can make the telescope much smaller for a given actual aperture, then you can make it a lot cheaper. So basically, the SuperSharp idea allows the telescope to be 10 times smaller in its launch configuration, and that actually makes it even more than 10 times cheaper. And the whole idea is scalable. So the original idea was for a 4.5 meter diameter payload, an Ariane, but it can be scaled all the way down to any rocket launch size you want. It's potentially a disruptive technology. And a really important point is that it is very, very useful for Earth observation. So this is what gives me hope about getting money for this, because this is a £10 billion market, maybe even more than that. Essentially, having intelligence and having accurate and up-to-date data about what's happening on the surface of the Earth is very valuable, especially to people, who make their money out of that sort of thing. So this is a big market, and therefore there are potentially a lot of wealthy investors who can help push this project along. So for example, you might be able to have 30 centimeters definition on the ground with continuous viewing. So there's always one of these things looking at you with that definition, as long as there's no clouds. You can have that with a constellation of nano-sats. And that, at the moment, there are constellations that give you 3 meters, but with this, you could have 30 centimeter, similar capability. Just to give some, and also it would work better at infrared wavelengths. Bigger telescopes mean the lambda over d is actually quite powerful at infrared wavelengths. I even mentioned balloons here, surveillance from balloons. So there's a lot of commercial applications. Of course, there are also many, many scientific applications, which I hope, which is the reason I really want to do this. I'm only thinking about this as a way of pushing the project forward. But ultimately, I'm interested in the scientific applications of this. So coming back to alternative funding sources, we're in a revolution called the New Space Revolution. I don't know if you know about that, but basically for the last 10 years, there's been more investment from outside of government space agencies than from the agencies themselves. So space is now really a commercial operation rather than a government agency operation. A lot of players now. And because of the Earth observation aspect and the value of that, it's possible to get grants from government on the basis of Earth observation cases rather than science cases. And indeed, we're also hoping that we can maybe even get money simply from investors who are giving money to us because they expect a bigger return on their investment somewhere maybe 3 or 4 years down the line. That's another possibility. And then in addition to that, access to space is now much cheaper and easier than it ever used to be, including something called the nano-sat revolution. So now CubeSats, small satellites can be easily launched for relatively small amounts of money. So this is a 3U. They basically come in units of 10 by 10 by 10. That's 1U. So this is a 3U. Here's a 12U, which is basically 4 of those. And just to bring home how big that thing is, I've put it next to an everyday object here. So you know what you're talking about. Okay, so, and just quickly to go through, forget about all the details in it. The important thing to look at here is the definition on the ground for Earth observation. So with a 3U, which costs about $250,000 to launch, you can get about 37 centimeters definition on the ground, so you can get something like pictures like this. With a 12U, you can go even finer. And with a 50 kilogram small sat, which costs only 1.7 million to launch, you can have a 2.5 meter telescope in space with ground definition of about 9 or 10 centimeters. So the costs are really coming down if this works. So how do we move forward with it? As I said already, we're seeking funds through non-astronomy routes. Milestone 1 is to work on this in the lab, and we're doing that. And so far, we've already received about 114K to do that in research grants. This is all Earth observation money. No, I'm not dipping into the astronomy budget yet. I'll show you where we got to with that in a second. Milestone 2 is the really important milestone. We need to put one of these in space and show to everyone that it works. And we think we can do that with a 3U version for about 1 to 1.5 million, maybe 2 million, something like that. And so that's something we're working on in terms of getting funding. And I think once that works in space, and people can see that cheap, powerful space telescopes are viable, then I think the scientific and commercial projects will just flow naturally from that. Okay, so where we are with the lab. So we're building an unfolding scheme. I'll show you a picture of a model we're doing. We've built a primary mirror segment which has all the actuators in it and fits inside a CubeSat. We're developing CubeSat models. I'll show you some of those in a minute. We've developed and operated a metrology system that allows us to get the data that tells us how accurately the mirrors are aligned. We have an actual working lab model of an actuated mirror, and we're currently building the software to make all that work together. So here's a picture of an unfolding CubeSat scheme that we're making as a model using 3D printed parts. But you can see here, this isn't just a cartoon anymore. We've got all the actuators inside this. So inside that thin, so this part here is the mirror surface. Of course, this is just a plastic version of it. We haven't made an actual optical mirror of this yet. But that has all the actuators to make that position at the nanometer level that we need. So that's it folded up. This is it unfolded. We have an optical test bed where we're phasing up these 3 mirrors. So if you have the PSF of one of them, it looks like that. It's just an airy pattern as you'd expect from a circular aperture. But when you superimpose all 3 of them on top of each other, you get this. And that shows you how combining these mirrors gives you the higher definition. Because the full width half maximum of what's in the middle here is much smaller than that. And that's where you get the high definition from. And so basically, this is a Zmax simulation. If you have 2 mirrors that are separated, it might look like that. And then as you bring them together, you start seeing the fringes. And here's a couple of pictures showing how we've actually done that in the lab. This is old data. Actually, we have much better data than this now. But that just shows what it looks like. Okay, so here's a picture of the technology demonstrator that we're designing. 3U, as I said. Basically, we're doing a 3U technology demonstrator because that's the least expensive way of doing the demonstrator. Okay. And so that's what it looks like. And this is quite a detailed model now. We're really starting to think about all the different parts of this machine that are needed to make it work. So that's what it looks like when it's folded. That's what it looks like when it's unfolded. And you can see here, this is the box that has the metrology system in it. This is the box that has the imaging system in it. That's one mirror there, that's another mirror there, that's another mirror there. So it's a 4-mirror cross system. And then here's an animation of that unfolding. So now the the whole unfolding scheme is driven by a single motor, so that everything is deployed from a single motor that pulls it all into place, like this. Okay. And then, just how much time have we got? This is what's going on at the imaging system. We're using a spherical primary mirror for this design. Horrible spherical aberration here, but then we correct that with these two mirrors. And then finally re-image onto a CMOS device here. And this is the metrology system that looks at the mirrors. So we can move the mirrors so that they bring the light together. But this is the two mirrors with incorrect tip tilt, but then when you superimpose them, you start seeing the fringes. So that's how we get the final thing. That shows the PSF of the thing. The MTF has all the information at the high spatial frequencies. So if it was a filled aperture, you'd have this part here, but that's what you lose by having a sparse aperture, but it doesn't matter because we're only interested in that bit. And then, for those of you who are more interested in science-type CubeSat mission, here's a version with 8 mirrors instead of 4, and a cartoon for that. I'm nearly finished. An animation for that. So I think this particular version could be used for really interesting science. Right? This is a 1 meter telescope in a 12U box. So this is a $1 million launch cost. Probably you could do the whole mission for $3 or $4 million, and you've got a 1 meter space telescope. That's extremely good value for money, in my opinion. Okay, so just to finish off, last one, sorry. So obviously we need high resolution imaging for astronomy. That's why we're here talking about it today. The life search is just one extreme science case. There are many, many science cases which require high definition imaging. This is best done from space, obviously. It's much better to collect the wavefronts before they've been messed up by the atmosphere. But of course, that's prohibitively expensive. Or at least that's what we have thought in the past. So the idea is, if you can make the telescopes more cheaply, maybe we can use space for high definition imaging much more. And so that would, if that's true, then that would lead to many interesting astronomy missions. It needs technology development to make this work. We just started it, and we're pushing forward to try and make the in-orbit demonstrator. And then ultimately, if it all does work, ultimately maybe this will all lead to the biosignature search mission, which is where I started the talk. Okay, thanks.
Okay, one very quick question.
Ian, when you launch these CubeSats, what sort of orbits can you get to, in as much as what's the orbital decay? What sort of lifetime could you expect for the orbit?
Well, it depends on how you go. Those numbers I gave you were for 550 kilometers up. They last for 5 years. Okay, and if you'd launched from the International Space Station, that's about 4. That's a bit lower, and they decay more quickly, like in a year or so. Yeah, but you can have wherever you want. I mean, these are basically being launched with bigger satellites, so they're just piggybacking on other missions, basically.
Okay, well, I think that draws everything to a close for today.